welcome back to a short series on the basics of performing density functional theory calculations, with a focus on modeling surface reactions. This series is based on the textbook Density Functional Theory, A Practical Introduction by David Scholl and Steckel, and also partly from my experience performing DFT calculations during my PhD research. In this episode, I'll discuss how we can use DFT calculation for modeling surfaces and identifying adsorption geometries. You might remember in an earlier video, I described how it's possible to simulate an entire crystal by repeating a single unit cell infinitely in all directions. This type of calculation makes use of what are called periodic boundary conditions. Under these conditions, an original unit cell is copied infinitely in 3 dimensions. The copies of this unit cell are referred to as images. At the right, you can see the original unit cell highlighted with a yellow background, surrounded by duplicate images. Under periodic boundary conditions, each of the cells interacts with its neighbor, which is an exact copy of itself. As you can see now, this also means that any particles leaving the cell immediately reappear on the opposite side with the velocity they had when they left. We can also take advantage of periodic boundary conditions to simulate processes at surfaces. For surfaces, the unit cell that we use contains atoms only along a fraction of the vertical direction, while the atoms in the lower portion fill the entire cell in the x and y directions. When this unit cell is repeated in 3 dimensions, it looks like a series of stacked slabs separated by empty space. For this reason, this model is creatively called the slab model. The empty space in the z direction that separates the slabs is called the vacuum space. When using the slab model, it's important that there's enough space between the slabs so that the electron density of the slab tails off to 0 in this vacuum region. This minimizes the unphysical effect of the top of one slab interacting with the bottom of the next. However, there's a trade-off. As the size of the vacuum space increases, so does the computational effort. In practice, you can determine how much vacuum space is enough by performing several calculations with slab models that have differing amounts of vacuum space. You can then check for which ones the charge density in the vacuum region is close to 0. As a starting point, typical vacuum spacings reported in the literature are around 20 angstroms. As you might have noticed, the slabs used in the slab model are very thin, consisting only of a few layers of atoms. Real surfaces, except in extreme situations, are the edges of a material that are at least a few microns thick. It's important that the slab model can mimic important characteristics of a real surface, but how many atomic layers are enough? Typically, as you might expect, the more layers the better, though more layers means a greater computational cost. The number of layers required to reach convergence depends on the type of material, as well as on the physical property being studied. Some property might converge with as few as 4 atomic layers, while another might require more than double that. As was the case with determining the ideal vacuum spacing, the ideal number of atomic layers can be found by changing how many layers there are and seeing how the property of interest varies. Once again, it's important to reiterate that the number of layers you use and the size of the vacuum spacing will usually be a compromise between physical accuracy and computational cost. So now that I've given an overview of the model we'll be using to calculate a surface, I'm going to take a brief aside to talk about the surfaces we wish to model. For starters, how do we define the surfaces we'll be working with? You can probably imagine that a simple way to get a surface is just to cut through a crystal at some angle, but there's many ways a cut could be made. Depending on how we make the cut, different kinds of surfaces with different arrangements of atoms will be revealed. To help enable our discussion of these surfaces, it'd be useful to have a notation allowing us to define precisely which surface we're considering. Let's consider a cut through a face-centered cubic crystal that intersects with the axes of the crystal's unit cell at the corners x equals 1, y equals 1, and z equals 1. For simplicity, these values are given in units of the lattice constant. Taking the reciprocal of these intercepts and then multiplying them by some scaling factor to ensure that each reciprocal value is an integer that's as small as possible, we arrive at the set of numbers called the Miller index that describes the plane created by the cut. Equivalently, these values also describe a vector that is normal to that plane. Here we see that the Miller index for this surface is 1, 1, 1. By symmetry, there's several equivalent ways to cut an FCC crystal that still produce an identical surface to this one. The symmetrically equivalent planes to the unit cell are grouped into the 1, 1, 1 family, denoted using curly brackets. The 1, 1, 1 family is particularly important for the FCC metals, as they have the highest possible density of atoms in the surface. But why would that matter? Well, surfaces with high atom densities are typically more stable, so this means they'd likely make up a large part of the surfaces of real crystals. Another important facet is obtained by a cut that intersects with the x and y axes at x equals 1 and y equals 1 and spans the entirety of the z-axis. In this case, the intercepts can be thought of as x equals 1, y equals 1, and z equals infinity. Taking the reciprocals of these intercepts results in a value of 110 or 110 for the Miller index. It's worthwhile for you to pause and consider how using symmetry you could obtain other planes in the 110 family. The final surface I'll show is formed by making a cut along one of the faces of the unit cell, here along the unit cell's top face. For this cut, the intercepts are x equals infinity, y equals infinity, and z equals 1. Once more, we take the reciprocals of these intercepts to get the Miller index, which here is 001. The three families of surfaces I've just shown you are now given here together for comparison. For these surfaces, an important characteristic is that they're all atomically flat. That is, in each surface, every atom has the same coordination as well as the same coordinate relative to the surface normal. Collectively, these three surfaces are referred to as the low-index surfaces of FCC materials. From these top-down views, it's also apparent that there are different symmetries for these surfaces. On the left, the 001 surface has fourfold symmetry. The distance between each atom on the surface is the same, and it's equal to the lattice constant multiplied by a factor of √2/2. In the middle is the 111 surface. The distance between each atom on the surface is also equal to the lattice constant times √2/2, though, for this surface, the symmetry is instead threefold. As you can see, the atoms of the 111 surface are also more densely packed together than the atoms of the other two surfaces. At the right, the 110 surface has the lowest density of surface atoms, and also has the lowest symmetry of the low-index surfaces, exhibiting only twofold symmetry. Additionally, for the 110 surface, there are also two different characteristic distances between the surface atoms. The larger of these distances is equal to the lattice constant, while the shorter distance is equal to the lattice constant times √2/2. This leads to closely packed rows of surface atoms along one direction, with each row separated by one lattice constant. The result is a surface that appears corrugated, in contrast to the smoother 111 and 001 surfaces. These examples represent only a tiny portion of possible surfaces, and I haven't even mentioned the complications that arise when you're dealing with compounds that don't have face-centered cubic unit cells. For the sake of time, I'll skip over these complications, though if you want some more information on how to deal with these types of surfaces, you can check out pages 91 to 94 of Scholl and Steckel's textbook. Now that you've got some background on how Miller indices are used to describe types of surfaces, it's a good time to bring up how we can describe features of these surfaces in more detail. We'll start with an anisotropic 110 surface as an example. If I want to describe to you where something is on the surface, like in what direction does a closed packed row of atoms lie, it's convenient for me to tell you this in relation to a surface direction. For finding this surface direction, we'll first note the points where the row of closed packed atoms intersects with the axes of the unit cell. Two such points can be found at 010 and 100. The vector that connects these 2 points can then be obtained by simply subtracting the coordinates of the initial position from those of the final position. This gives us a vector with an x component of 1, a y component of -1, and a z component of 0. By convention, negative signs are denoted by an overbar, so we can say that the closed packed row lies along the 1*10 direction. Now there's no particular reason why the initial and final points couldn't be reversed. You could just as easily say that the closed packed direction is *110, as by symmetry, the 1*10 and *110 directions are identical. It's just that 1*10 sounds much nicer than *110. Okay, so what about the direction that points perpendicularly to the closed packed direction, where the spacing between the atoms is larger? Again, the simplest way to do this is to identify 2 points along this direction that intersects with the unit cell. 2 such points are 010 and 011. Subtracting the coordinates of one point from the other, we get 001, or equivalently 00*1 as the perpendicular direction. I'm not going to get into why, but I'll just tell you that the 1*10 and 001 directions are the ones you most often see given for the 110 surface. It's pretty easy to get the 1*10 and 001 directions, as they had start and end points coinciding with the corners of the unit cell. What about for directions where this isn't the case? Like, for example, a direction that's somewhere between 1*10 and 001. Let's say it has a starting point of 010 and an ending point of 1/2, 1/2, 1. If we follow the same procedure we've used before, we arrive at a vector with an x component of 1/2, a y component of -1/2, and a z component of 1. This is cumbersome to say, let alone to write, so the next step we want to take is to simplify this vector by multiplying it by some scaling factor to ensure its components aren't fractional values. Multiplying this vector by 2 does just that, giving us a surface direction of 1 bar 1, 2. I'll leave it to you as an exercise to hunt for the different directions on these low-index surfaces. As a start, you should try to identify the 1 bar 1, 0 direction on the 0, 0, 1 and 1, 1, 1 surfaces. For now, I'll get back to how we can set up a calculation to model these surfaces. Near the beginning of the episode, I mentioned that surfaces can be modeled by repeating a single unit cell infinitely in space. What you see here is an example of how we might build a unit cell with 5 atomic layers to model a copper 110 surface. The dimensions of the supercell are given by the supercell vectors a1 through a3. It's straightforward to see where the vectors come from. The vector a1 points along the 0, 0, 1 direction, which happens to also lie along the x direction. There's no particular reason for this, as it could just as easily point along the y direction, or partway between the x and y directions. I've simply chosen this for convenience. The vector a2 points in the close-packed 1 bar 1, 0 direction, and is conveniently aligned along the y-axis. The magnitudes of these vectors are equal to the unit cell size in these two directions. The value a is the ideal bulk lattice constant that was calculated in a previous episode. It's important when you perform calculations to report the value of a that you used. The third vector, a3, points along the z-axis, which is often the same direction as the surface normal. The magnitude of a3 is the sum of the slab thickness and vacuum spacing. Okay, so now we have the unit cell dimensions. How about the positions of the copper atoms? We can take a look at the FCC unit cell to find out. I'll highlight the relevant copper atoms that we're dealing with. We can clearly see that copper atoms 0, 2, and 4 lie along a close-packed direction, so they must have a spacing of a over root 2 between them. In building the supercell for the slab, I've decided that the z-axis will lie along this close-packed direction. So, starting from copper 0 sitting at the origin, copper 2 must have a z value of a over root 2, and copper 4 must then be 2 times a over root 2. You can check the math. But what about copper 1 and copper 3? We see that these two coppers also lie in a close-packed line, which is parallel to the other 3 atoms. However, they are offset along the z direction by a value of half of a over root 2. This means that the z value of copper 1 has to be half of a over root 2, while copper 3 is 3 halves of a over root 2. Hopefully, you could follow me through that, but conceptually, that was the hardest part. Coming back to the top-down view of the surface, it's much easier to see where the x and y positions come from. As I said earlier, coppers 0, 2, and 4 lie along the z-axis, which for convenience I placed at the corner of the copper 110 unit cell. This means their x and y values are 0. Coppers 1 and 3, however, sit in the middle of the unit cell. This means they must have an x position of half of a and a y position of half of a over root 2. A good exercise for you to try is to build a 2x2 supercell, that is, a supercell that is 2 unit cells wide in the 0, 0, 1 direction and 2 unit cells wide in the 1 bar 1, 0 direction. Can you identify the correct x, y, and z coordinates for the 15 additional copper atoms? Also, you should think about how the supercell vectors will need to change for this larger supercell to repeat in the x and y directions without the atoms overlapping. Now that you've built your supercell, we can get into the details of how to set up a calculation with it. As these slab model calculations are conducted using periodic boundary conditions, they can make use of the Monkhorst-Pack method for choosing k-points. The main thing to remember when choosing the number of k-points to use is that when it comes to convergence, it's the k-point density that matters. This means you'll have to make sure that the density of k-points in each direction is similar to allow for a well-converged calculation. But how do you ensure that each direction in k-space has a similar k-point density? Say we have a rectangular slab supercell with the following dimensions: 2 units in A1, 4 units in A2, and 20 units in A3. As distances in real space are inversely proportional to distances in reciprocal space, this means that large distances in real space correspond to small distances in reciprocal space. As a rule of thumb, dividing 2 pi by the magnitude of the real space vector will give us the size of the corresponding reciprocal space vector. So the sizes of the corresponding reciprocal space vectors are pi for B1, pi over 2 for B2, and pi over 10 for B3. Comparing the sizes of the reciprocal dimensions, we see B3 is 10 times smaller than B1, and 5 times smaller than B2. This means that we need 10 times as many K-points along B1 and 5 times as many K-points along B2 compared to B3 to have a similar K-point density along each direction in K-space. So how many points do we actually need? Well, if the vacuum region is large enough, then the electron density will tail off to 0 a short distance from the edge of the slab. This means accurate results are possible to obtain using just one K-point in this direction. So for this particular supercell, a good starting point would be a 10 by 5 by 1 K-point mesh. The next step forward is to ensure that the surface layers of our slab model are relaxed. What does that mean? It's important to realize that atoms in the surface of a material are less coordinated compared to those in the bulk. Because of this, the spacings between atomic layers near the surface will differ compared to those in the bulk, though this difference in spacing is on the order of a few tenths of an angstrom. The reason this phenomenon is referred to as surface relaxation is that when the surface is relaxed, it's lower in energy. We can get the geometry of the relaxed surface by minimizing the energy as a function of the positions of the atoms in the supercell. We imagine that the bottom of the slab represents the bulk of the material, so we constrain the atoms in these layers to their ideal bulk positions. The atoms in the top layers are then allowed to move in order to minimize the energy. You should find that during relaxation, the atoms in these top layers will only move in the z direction. This behavior makes sense from a physical perspective, as by symmetry, the force on the atoms in the plane of the surface should cancel each other out, leaving only forces pointing along the z-axis. The change in distance between layers of a relaxed and unrelaxed surface is denoted by a delta, with the change between the first and second layers being delta 1, 2, between the second and third layers delta 2, 3, and so on. The changes in interlayer spacing are often expressed as a percentage of the bulk material layer spacing, with negative values representing contraction and positive values representing expansion. Increasing the number of atomic layers you use in your relaxation calculation can lead to better converged results, though, as always, your trade-off is increased computational cost. Up to this point, I've only focused on clean surfaces, which is to say, surfaces with the same chemical composition as the bulk. However, most of the interesting processes occurring at surfaces happen when other chemicals are present on them. When atoms or molecules stick to the face of a surface, we say that they're adsorbed on the surface, and we call the adsorbed species adsorbates. But how do we tell where these adsorbates prefer to stick? If we look at the 1,0,0 surface, we notice there are several sites with special symmetry that seem appealing as potential binding sites. These are the top, bridge, and hollow sites. How can we tell which of these sites is more favored by the adsorbate? As you might guess, we can do calculations where we place the adsorbate at these positions and then minimize the system's energy by allowing the positions of the adsorbate and the first few layers of the slab to relax. By simply comparing the total energies we obtain from these calculations, we can identify the most stable adsorption configurations, since the differences in total energy correspond to the energy cost, or gain, in moving these adsorbates between the various sites. That's it. Job's done. Or is it? We need to be sure that the adsorption geometries we've identified are indeed local minima instead of the adsorbates being trapped at a local maximum due to symmetry. We can determine this by performing a relaxation calculation where the adsorbates start slightly displaced from the high symmetry positions, then observing where the adsorbates go. If they go back to the high symmetry position, it's a local minimum. If they leave, it was probably a local maximum. It would also be nice to have an indicator for just how strongly the adsorbates are stuck to the surface. A good indicator for this is the adsorption energy. The adsorption energy is typically obtained by subtracting the total energies calculated for a clean surface and for a gas phase molecule from the total energy calculated for the adsorbate on the surface. The physical meaning of this quantity is that it is the amount of energy required to pull the adsorbate off of the surface. If this quantity is a negative value, it means adsorbing on the surface in this particular way is favored compared to the molecule being in the gas phase. The more negative the value, the more favored the adsorption is. On the other hand, a positive value for the adsorption energy means that the molecule would much rather be in the gas phase than on the surface. The last thing to keep in mind when modeling what's going on at the surface is the size of the unit cell you use and what that means for the surface coverage. Imagine we want to model an atom that's adsorbed at a fourfold hollow of a 001 surface. We'd probably want a unit cell similar to this one, right? Well, If we tile this unit cell out, we find it actually leads to a high coverage on the surface. This coverage is known as a monolayer, as every possible adsorption site is filled by an adsorbate. Maybe we don't want to model a monolayer coverage. Maybe we want a slightly larger spacing between adsorbates. What if instead of every hollow being filled by an adsorbate, every other hollow was? Tiling out this unit cell, we can see that it leads to a coverage of half a monolayer. Interestingly, it's also possible to achieve the same coverage using a smaller unit cell. Why might this be desirable? Well, a smaller unit cell means fewer atoms, which means a cheaper calculation. Doing these calculations for yourself, you're also likely to see the trend that the lower the coverage, the greater the computed adsorption energy. This is from the strength of interaction between neighboring adsorbates decreasing as they are separated. It also means, for most calculations, you can't ignore the effect of neighboring atoms. I think that's enough information to set you on good footing to perform relaxation calculations and hunt for adsorption geometries on your own.